In this experiment, we measure the neutral temperature of iron-copper thermocouple. There are three thermoelectric effects: the Seebeck effect, the Peltier effect, and the Thomson effect. If a wire of a metal is held at a temperature T plus delta T at one end and a lower temperature T at the other end, an EMF appears between the two ends. This EMF is proportional to the temperature difference delta T, so it is given by S delta T, where S is called the Seebeck coefficient. How does it arise? Electrons at the hot end have a higher kinetic energy and higher velocity than electrons at the cold end. So, more electrons from the hot end come towards the cold end than electrons going from cold to the hot end. So, there is an accumulation of electrons at the cold end and a depletion of electrons at the hot end. This produces a voltage difference and an electric field which opposes the motion of electrons from the hot to the cold end and aids the motion of electron from the cold to the hot end, till the electric field balances the effect due to temperature difference. When that happens, the number of electrons crossing from right to left and left to right become equal. So, it is this accumulation of electrons which is responsible for the thermoelectric effect. Let us take a junction of two different metals. We can make two junctions of these metals and we maintain one junction at a higher temperature compared to other junction. If we insert a voltmeter here in one of the lands, then a voltage will appear, and this voltage is called the thermoelectric EMF of the thermocouple made of A and B. This voltage will be equal to Seebeck coefficient of A minus Seebeck coefficient of B into delta T, that is SAB into delta T. SAB is called the thermopower of the thermocouple made of A and B. The Peltier effect is the following. If we pass a current through a junction of two metals at a temperature T, heat is absorbed or emitted at the junction depending on the direction in which the current is flowing, whether it is flowing from A to B or B to A. The amount of heat liberated in unit time is given by the current multiplied by the difference in two quantities pi A minus pi B, where pi A is called the Peltier coefficient of metal A, pi B is the Peltier coefficient of metal B. You can use this effect for producing thermoelectric refrigeration. The Peltier coefficient and the Seebeck coefficient are related. The Peltier coefficient of metal A is the absolute temperature of the metal into Seebeck coefficient of metal A. if only the Peltier and Seebeck effects existed, then Thomson showed that the thermo EMF of any thermocouple must increase linearly with temperature. But we find that the thermo EMF of iron copper increases, the increase becomes slower and slower, it reaches a maximum value and then it decreases. This contradicts the result that thermo power must increase linearly. So Thomson predicted that there must be a third effect, thermoelectric effect. When a current flows through a material in which there is a temperature gradient, there is a reversible generation of heat given by Q is minus mu I into the temperature gradient. Mu is called the Thomson coefficient. Mu is related to the temperature derivative of the Seebeck coefficient. If mu is 0, S is constant and thermo EMF will increase linearly with temperature. If mu is not 0, the thermo EMF will not increase linearly with temperature. So this experiment on iron copper is a very important experiment, and we thought the students should do this experiment. I have here 4 wires, 1, 2, 3 and 4. The 4 wires pass through holes in a porcelain rod, so that the porcelain insulates the different wires. We have chromal alumal wire, we have iron copper wire. The iron copper wire is connected to this terminal, and the chromal alumal is connected to this terminal. The 4 wires are welded at the bottom end, and the welded end is hanging inside a furnace. I connect the furnace to a transformer power supply which can give 10 volts AC, 25 volts AC, 40 volts AC. If I put this switch in 25 volts, a current will flow through the heater coil and furnace will become hot. So the chromal alumal will show a thermo EMF, iron copper will show a thermo EMF. Chromal alumal is connected to channel 1, iron copper to channel 2, and we put this switch to 25 volts, switch on, see what happens in channel 1. You have to wait a bit because heat takes time. You see, thermo EMF of iron copper thermocouple is going up fast. At the same time, thermo EMF of chromal alumal, this is chromal alumal, it is going fast. Same time, thermo EMF of iron copper is also increasing. So all that you do is, every 5 minutes, you take the reading channel 1, take the reading channel 2. Every 5 minutes. Channel 1 gives thermo EMF of chromal aluminal in millivolts. Channel 2 gives thermo EMF of chromal iron copper in millivolts. Take the reading every 5 minutes till the chromal aluminal reading reaches a value 14 millivolts or 16 millivolts. That means 16 millivolts means that the welded spot is at a temperature 400 degrees above room temperature. So, if room temperature is 30, temperature of the spot is 430 degrees. So, continue the experiment till channel 1 shows 16 millivolts. Then switch off the furnace and switch off the millivoltmeter. The chromal aluminal thermocouple is used to measure the temperature because its thermopower is constant, independent of temperature, and has a value 40 microvolts per degree centigrade. So, if channel 1 you have a voltage V millivolts in channel 1, you multiply it by 1000 to convert to microvolts and divide it by 40 to get the excess temperature above room temperature. So, 1000 by 40 is 25. So, multiply V1, this is 1 millivolt, then 25 into 1 plus room temperature. So, room temperature is 30, temperature now is 55 degrees centigrade. So, you can from channel 1 reading you can calculate the temperature, then plot channel 2 readings in millivolt against temperature. You see that thermo EMF of iron copper increases, reaches a maximum and then comes down. You fit this to a second degree polynomial equation A plus BT plus CT square, find A, B and C. You will find C will be negative, B will be positive. You differentiate this equation, find dV2 by dt, that is B1 plus 2B2t, or BB plus 2CT. I wrote here B and C, so this will be B plus 2CT. So, at each temperature you can calculate thermopower of iron copper, because you know B, you know C, so you can calculate this. Plot the thermopower of iron copper against temperature. It goes to 0 around 250 degrees centigrade, that is the neutral temperature of iron copper thermocouple. That is the temperature at which the thermopower changes from plus to minus. Thermopower of iron copper is Seebeck coefficient of iron minus Seebeck coefficient of copper. Seebeck coefficient of copper varies as alpha plus beta t, where alpha is 1.7 microvolt per degree centigrade, beta is 4.99 nanovolt per degree centigrade square. So, from this calculate S copper at all these temperatures, you have calculated S iron copper, add S copper to S iron copper, that gives how the Seebeck coefficient of iron varies with temperature, and you see Seebeck coefficient of iron is coming down, Seebeck coefficient of copper is going up, and where they intersect, this difference is 0. That is the neutral temperature.